Hey, welcome back to the Weather Whiteboard. Today we'll be discussing large-scale weather patterns and basically get a better understanding of how our weather moves, both horizontally and vertically and across the globe. So before we dive into large scale, let's review a few paradigms of Earth's atmosphere and the energy that drives our weather. So you've probably heard me talk about this before, but first and foremost, it is the sun is the source of the energy, and it's what drives our weather. A key word is what's called insolation, which means incoming solar radiation, and so that's the incoming solar radiation. That's going to be your UV energy that provides the heat that drives our weather. Number two, the tilt of the Earth creates the season. That 23.5-degree tilt. It's more about that than the distance of the Earth from the sun, because we are actually closer to the sun during our winter in the northern hemisphere than we are during our summer. But because of the tilt towards the sun in our summer provides more direct insolation, plus the radiation from the sun to the Earth is moving through a vacuum, so that extra several million miles really doesn't change the reduction or increase in energy. Keywords again to look up if you don't know are solstice, equinox, the perihelion and aphelion. And perihelion and aphelion are the times when the Earth is closest to and furthest away from the sun. Again, irregular composition of Earth. What I mean by that is that because the Earth is made up of both water and land, and there's more land in the northern hemisphere and the southern hemisphere, it may impact weather. How close you are to a large body of water is going to impact your weather. Even surfaces such as concrete, the urban heat island effect of being, high concrete, high asphalt buildings that block the wind. You're going to be warmer there than the surrounding areas. Areas, again, that are high albedo, high reflectivity, white sand, snowy areas are going to reflect more of the incoming solar radiation. Specific heat, again, just meaning water requires more energy to change temperatures, to increase it or decrease it. So that's why when you live near or you're near a large body of water like Lake Erie or an ocean body, you're going to have more moderate temperatures, less fluctuation, because the water is going to insulate the shoreline. As you move in more inland, you have less water. Because the ground has less water than the ocean, it's going to change temperatures a lot more rapidly. So that's why you get greater fluctuations. We used that example once before of like San Francisco and St. Louis, and even though they're basically in the same latitude, San Francisco never gets nearly as warm or nearly as cold as St. Louis, which gets much hotter and much colder through the seasons, just because of its proximity or lack of proximity to water. High pressure, low pressure. Again, high pressure means cooler, sinking air. Think of it pushing down on your shoulders. It's cooler, it's sinking. Stable, we'll talk a little bit more about what stability means. It's generally drier because cooler air has less ability to hold moisture, provides better weather. Cirrus clouds generally are high, thin, wispy ice crystals. Terms divergent and convergent. So divergent means it's going away. So a high pressure system, the air sinks, it comes to the surface, it comes out, which means it's diverging, it's going away. It's like dumping a bucket of marbles out on the ground. They come down, boom, they spill in all different directions. So they're diverging at the surface. And because of the Coriolis force, which turns things to the right in the northern hemisphere, as they move away, they're actually moving away and making right-hand turns. And that's what creates that clockwise, or in your view, the clockwise rotation of a high pressure system at the surface. And then the low pressure is just the opposite. Low pressure is unstable, meaning it's warmer, rising air, generally more moist, creates more volatile weather, gets those towering cumulonimbus clouds, and it is converging. So because the low pressure is going up, it creates a void near the surface of pressure. It's low pressure. So then the high pressure is moving inward or converging at the surface. So it converges, goes up, and then diverges at the top, but converges because it's coming in and turning right, makes that right hand turn. That's going to create that counterclockwise, or what's called cyclonic rotation. So just understand the terms of convergence and divergence, and a lot of times the questions will reflect to if it's at the surface or in the upper atmosphere, because it's the opposite, high above in the upper atmosphere. Air flows like fluids. It's going to flow from high pressure to low pressure. So if you see a high pressure system and a low pressure system, grab my pen. It's going to, as it comes out of the high pressure system, it's moving towards the low pressure system. But it's also turning right as it moves out all the way around. It'll flow from high to low. The more these lines, these isobars, the greater the pressure gradients, the more intense the wind's going to be. Understand the Coriolis force, which is stronger at the poles, near the poles, and weakest at the equator. So if we're mid-latitudes, we got kind of the middle strength Coriolis force. Here's just a snapshot of a isobar map. So again, isobars are lines of equal or constant pressure. They're separated by every 4 millibars. That is the measurement, the unit of measurement for pressure for meteorology. And they never intersect. Sea level is 1,013.25 millibars. So these are tons. There's a ton of the isobars here. So we got a really huge pressure gradient coming in this direction. This is a low pressure system, so everything's moving at a 45-degree angle off these, no matter where you track them, which creates that counterclockwise rotation known as cyclonic. All right, properties of water. You should know all the phase changes, the difference between melting and freezing, between evaporation and condensation. And a couple of the big ones is deposition, or deposition and sublimation. So sublimation is really when you kind of skip a phase. Sublimation is when you go straight from ice to a vapor. And sometimes you might even see that when you're looking over a frozen body of water and it looks like steam coming off the ice. That's actually water sublimating straight from a solid to a vapor. And then the opposite is true. You can have what's called deposition when you go vapor straight to ice or a solid. Sometimes this forms in the surface. That's what you call riming. Another thing just to understand, there's a term over here. It's called latent heat. If so, you can actually have water, let's say, at both a liquid and a vapor, both at the same temperature at 100 degrees Celsius or 212 Fahrenheit. But there's an extra bit of energy that requires it to make that jump. So if you have liquid water and you need to, right at the boiling point, you have to add that extra heat for it to make that jump. It needs that extra energy to jump from a liquid to a gas. All right, so that's called latent heat of vaporization. That's 450 calories. So the opposite is true then when it drops down from a vapor to a liquid. And that's really important when we start thinking about clouds and what's happening as rising air masses, is that when you have water vapor, when it drops down to a liquid form, as its phase change, it actually releases this latent heat. So you have a cloud that's rising, and it's cooling adiabatically. Remember, adiabatic cooling, it rises, there's less pressure, so it expands, so it actually decreases the temperature without any really external forces. But as that cools and that vapor drops down to a liquid, it actually releases heat, which actually helps that to continue to rise. So that latent heat release at condensation actually helps continue the rising of that air parcel. So the term stability and instability, and yes, that's a typo. But so an air mass that's stable will either want to stay where it is or sink, where unstable air mass is rising. And it's, unless it's being forced to rise by other means. And how could it be forced to rise? Well, one could be what's called orographic lifting, where you have a air mass coming, let's say, off the lake, or off, let's say you're in the Pacific Northwest and coming off into Washington State, and it's a continental maritime polar air mass. All right, there you go, coming off Pacific Northwest, comes in, and then it hits the Cascades, and then it hits that mountain range. So it's actually forced up. It's forcing it up. So it's not really rising on its own because it's more buoyant, but it's being forced up. So that's called orographic lifting, when it's being forced up over a geographic structure. The other way would be if a air mass is just sitting here and a cold air mass comes into it, which again is more dense, heavier, running along the ground, and it forces it up. So, meaning if you took that cold air away, it would come back down. But so unstable air mass is an air mass that wants to rise on its own due to buoyancy. Basically, it's warmer than its surrounding air, be more volatile. All right. Okay, so we talked a little bit about adiabatic heating and cooling. So what does that mean again? So if you have an air mass that's here, and as it rises because of decreased pressure around it, because there's less air above it, it will expand. This happened to me once on vacation. Once I think I had a bag of potato chips unopened, and as we were driving up a peak, actually the bag of potato chips actually began to expand because the pressure inside the, because there's less pressure outside as we went up the mountains, the air inside began to expand. And really the interesting thing is if you open the bag of potato chips, they're actually colder inside than in the outside temperature. So adiabatic heating and cooling is basically based on pressure as you go up and down. As it comes back down, as an air mass begins to sink, it gets compressed and it will get warmer without adding any heat externally. Just because it's compressed, all the molecules have less room to move around, more collisions, heat. That's adiabatic heating and cooling. Then there's a term what's called the lapse rates, and there's actually 3 of them. And we're going to do a little walkthrough here. So number 1, there's what's called the environmental lapse rate. What's the environmental lapse rate is that general trend of what the temperature changes as you go up in altitude. And generally considered to be the environmental lapse rate is 3.5 degrees Fahrenheit for every 1,000 feet. So if you were going up from sea level to 10,000 feet, that's a 35 degree temperature change from sea level up to that peak. So if it was 75 degrees when you started and you got to the peak, it's going to be 35 degrees up there. That's called the environmental lapse rate. So there are 2 ones when you look at more like when you're looking at an air parcel. It's called the dry adiabatic lapse rate and the saturated. So it's going to be dry, even though it's not perfectly dry, but it's considered dry until it's considered saturated. It's saturated when the temperature and the dew point are going to be the same temperature. So that's going to be the rate that those rise. So as it's going to be dry, dry, dry until it's saturated, and then it changes to the saturated lapse rate. So I will walk you through this. So up in the top left corner, again, we have the dry adiabatic lapse rate, the environmental, and the saturated. So here's a little walkthrough, and you can pause this if you want to. So here's our air mass sitting at the ground. And the air mass inside the little circle, that air is 80 degrees with a dew point of 58 degrees Fahrenheit. And the air is out, you're at sea level, and the external temperature, or the surrounding air, is 70 degrees Fahrenheit. So something, maybe because there's clouds and something peeked through, and this air mass could be, a quarter mile, a mile wide. It's not necessarily just this little ball, but maybe, the clouds parted and you have more insulation hitting this area than the surrounding area to heat that up. So fill in the blanks first. So if we have 2,000, 4,000, 6,000, 8,000 feet in elevation, and we know, first we would do is we would calculate the environmental lapse rate. So we go up here again, it's 33.5 degrees Fahrenheit per 1,000 feet. So for every 2,000 feet, that would be 7 degrees Fahrenheit. So for every 2,000 feet we go up, the temperature is going to go down 7 degrees. So at 2,000 feet, so what would that be? 63. What about 4? We'll just fill in the blank. You can pause this if you want to check your math before we go. Keep going up a little harder. And at 8,000 feet, the environmental temperature would be 42 degrees Fahrenheit. So now let's look a little bit more specifically about the actual air mass. So it's 80 degrees where the external temperature, out the surrounding temperature is 70. So it's considered to be an unstable air mass because it's going to be more buoyant and it's going to want to rise. Right? Again, and as it rises, it expands adiabatically. Less pressure, it's cooling and expanding adiabatically. Right? So if it goes up, and now because we're using, it's considered the dry adiabatic lapse rate. Because until this are the same as the dew point, we're going to use the dry adiabatic lapse rate. So what would you think the temperature would be at 2,000 feet up inside the parcel? So it's going to be 69 degrees. So if we use the dry adiabatic lapse rate, so that's 5.5 degrees per 1,000. So that's 11 degrees for every 2,000. So it's going to decrease by 11 degrees. So now that air mass at 2,000 feet is 69 degrees. And the dew point doesn't change. It stays the same. It's still 58. So then we make the next jump up to 4,000 feet. It expands a little bit more adiabatically, cools adiabatically. Next temperature is going to be 58. So, something interesting happens is there, that the temperature of the air mass is now at the dew point. So what happens? Clouds develop because you're going to go from the air mass is now saturated. So it's any point above 58, any cooler point, you're going to have a phase change of some of the vapor. That air mass can no longer hold the moisture, so it's going to begin to drop out and condense. And again, going back to that latent heat thing, now even though you're going to get cloud development, there's latent heat added back into that. That's going to help it rise a little bit more. So now up at 6,000 feet, again, the air mass expands even more. And the temperature decreases now, though, because it's saturated. We're going to use the saturated, also known as the wet adiabatic lapse rate. You'll see that as well. But because it's saturated water, again, that specific heat of water is so much higher, it takes more energy to either increase or decrease it. So it's going to slow the rate at which it loses its temperature. So now you're there at 2.7 per 1,000. That's 5.4 per every 2,000. So 5.4. So as you see now, that it's going to decrease. Its rate of decreasing temperature is going to slow because it's saturated. You're going to have clouds. And the same thing as you go up to 8,000 feet, and it continues on. So that's how you would plug in and understand how the environmental lapse rate works, how saturated versus dry works. And those are very similar testable pieces of information you'll see. All right. The 3-cell model. We've covered this several times, but it's great to review. Again, there are 3 cells in the 3-cell model. That's why it's called the 3-cell model. The Hadley cell, which basically runs from the equator to 30 degrees. It's considered the tropical cell. It's the warmest. It's the largest because that's the largest circumference of the Earth. So the Hadley cell is the largest, considered the tropical cell. And again, that it's a model, but the cells will move north and south through our season. So like for us in the northern hemisphere, the northern Hadley cell will float to the north a little bit more during our summer and back near the equator during the winter. And so will all the other cells. The major wind belt of the Hadley cell is the northeast trade winds. Ferrule cell, which is considered the mid-latitudes. We live in the ferrule cell here in Ohio, 30 to 60 degrees of latitude approximately. The major wind belt is the westerlies. And the call them the westerlies. It's a little bit more southwest and northeast, but we consider them the westerlies. Again, we have moderate Coriolis force here in the mid-latitudes. The polar cell, 0 or 60 to 90 near the poles. The polar easterlies are in an extreme east-west because you have such strong Coriolis force there. The transition zones between the two is called the intertropical convergence zone, the ITCZ, also known as the doldrums. And why it's intertropical, it's between the northern and the southern Hadley, which are the two tropical cells. So it's the intertropical convergence where they come together, convergence. It's an area of extreme low pressure because it's so warm there. So warm air, that's why the big L's there. Warm air constantly rising, very hot, very moist. And the doldrums is considered plus minus 10 degrees on either side of the equator, depending on the season. Again, an area of very low pressure. The subtropical jet, aka the horse latitudes, is that area between the between the Hadley and the Ferrel cell. It's about 30 degrees. It's an area of high pressure. Again, you have sinking air there, and so this spreads back out, and that creates the wind belts in both directions. You have the subpolar jet, which is also the separation between the Ferrel and the polar cells, also known as the polar front. And just a little bit about jet streams. Again, they're meandering, and those waves. So it's not a straight line. So they're meandering. They're called Rossby waves, and both our jet streams move from west to east. They're great to fly in. And again, they will ebb and flow north and south during the season. So they'll go a little bit further north during the winter and a little bit further south summer. But they also have less waves in the summertime. Air masses. Again, air masses are defined by two characteristics. If they're formed over land or water, so land means dry, water means moist, and then temperature, or they're cold, cooler, or they're moist. So they're basically given a name by their point of origin, and those two things will define their composition. And so the first one being continental or maritime, and they're always written with a lowercase letter. So continental is formed over land, so land has less moisture, so it's dry. A maritime, think of like a mariner, like on the water, it's formed over water, so they're moist. And again, those are written with either lowercase c or m, and that's the first letter, followed by the temperature one, P for polar, formed in the upper latitudes, which means cold. T for tropical. Tropical means warm, not moist, formed in the tropics. And there's one seldom used, it's the Arctic, which is formed in very extreme cold temperatures. So if you had a continental polar air mass, it was formed in the upper latitudes, so it's cold and dry, basically. Maritime tropical, moist and wet, and that's pretty much that's really what you need to know about that. Remember that cold air is more dense than warm air. Cold air moves faster than warm air. The coldest of all air masses then would be cold and dry, because dry air is actually more dense than moist air. Weather fronts. There's several here in the drawing. A front really defines, what side of this boundary, if you will, that type of air mass is. And when you see the little symbols, let's also remember that here's a cold front. So number one, very symbolic, cold being blue, red being hot. The little diamond shapes I always refer to as little icicles hanging there. So cold front. And the thing to remember about this line is the cold air is here, and the warm air is on this side. So it tells you what direction it's going. So again, we see a stationary front, which means there's pretty much a Mexican standoff, if you will. One's not overtaking the other, or they might even be moving laterally to each other. So a stationary front, say, again, the cold air is here, trying to go this way, whereas the warm air is on this side, trying to go this way. So those are things to remember about fronts when you see them on a map. So the cold front is fastest moving. It's usually more intense. You see the most intense storms because the cold front, think of like it's a little snow plow coming along, and it's going to force the warm air up as it moves along. The warm air is going to usually have more moisture. So cold fronts move faster, and if you look at a map, you see a big line of storms. It's probably the cold front is right behind that line, pushing stuff up and creating those storms. Warm front usually it's preceded by the cirrus clouds, but again, because if there's cold air mass here and the warm front's coming in, because it's riding up, even though it's pushing it, it's riding up on the cold front. The warm, moist air, the first part that's going to arrive is the upper air, and as it comes closer to you, then you'll get more warm air coming to the surface. So cirrus clouds precede the warm front. There are ice crystals up there. An occluded front is when a cold front actually catches up to and begins to overtake a warm front, or yes, a warm front trapped between two cold fronts. The stationary front, again, is basically they're sitting next to each other, but one's not overtaking one. And that's usually when you're going to get those really long, slow, drizzly kind of rains. The most intense storms are going to be in front of a cold front. Second most are usually going to be in front of an occluded front. In a dry line or a dew point front, just that, it's actually a front that distinguishes moisture on one side or the other, not necessarily temperature. You'll see those in the Southwest a little bit. And actually tornado hunters like to look for dry line fronts because you do get a lot of storms along dry line fronts as well. So weather fronts here again, some pictures. Here's your classic cyclogenesis. You have a low pressure system here. So you have counterclockwise rotation. Probably going to get a storm out in front of here. This moves faster. It's going to eventually wrap around, catch up. You might get some occlusion, or this acts like a little bit of zipper here. And then as the warm front moves further north, you might get precipitation or snow out front of that, depending on the time of year and where it's happening. Already went through these. So here's a diagram of a cold front. Again, cold air, very moist or very dense, moving this direction, which is forcing the warm air up. And that's why the storm's going to be right out in front of here, generally speaking. You can see the temperature differences here on your station models. That's going to define that front. Your warm air, again, even though it's sometimes your cold front, cold air might be stalled out, so your warm front's moving along. That's what I mean when the cirrus clouds show up first, because the warm air aloft is going to arrive before the surface warm air. Your occluded front, again, you might have cold air here, colder air here, and it's kind of trapping the warm air between. And this is probably the second most intense storms come along an occluded front. Your stationary front is a cold air front and a warm air front. They're setting next to each other. Sometimes there may even be moving lateral to each other. And those are those like this long drizzly kind of storms. Your dry line front here, if you were going to look at, if you had station models on both sides here, what you probably see is the dew points on the moist side. Let's say it was 70 degrees and this was 70 degrees over here. The dew points here might be 68. The dew points over here are going to be 30, which tells you this is drier air than over here. You can still get pretty intense storms along the dry line front. So this is a current, we call this a classic weather map. It's a synoptic scale. Remember, synoptic means basically the entire country. You have micro, macro, mesoscale. Mesoscale like the size of the state, and synoptic, and then lastly is global. So what do we see here? We see some major low pressure system here. You have pressure moving from high pressure to low pressure in both directions. So you have converging at the surface. You have counterclockwise rotation here. This is a cold front. You have probably continental polar air coming down here. You're probably going to start to develop an occlusion here. And yeah, and then all the weather again is moving kind of in this direction across. So even though it's rotating here locally, the entire weather is moving southwest to northeast. And one more map. So again, occluded front here. This cold front continues to wrap around. You have a little stationary because you have some maritime tropical air coming in here. So you have warm air in this direction. Sometimes you'll see dry line symbols as this versus the one that has a little brown bumps on it. Yeah. So not a whole lot happening here, not too many isobars, so everything's kind of the same temperature. So that was a great review. Look forward to seeing you on some of the other whiteboards, and we'll see you soon.